right, so we get -2. I'm going to skip 0 for right now. When we plug in -1/5, get 1 over 1/5. And I think Jen in the chat just asked if I have a good fraction refresher video, or she asked if anyone else does. I don't. I would probably just look on Khan Academy, but if someone else does and they want to put that in the chat, that would be good. All right, and for 1/5, we'll actually derive out why it's going to end up being 5. We can think about it as this is just like fraction division, where we can say 1 over 1 is a fraction. It's the same as 1, and we're dividing by 1/5. And then that's the same as 1 over 1 divided by 1/5, which is 1 over 1. And we multiply by the reciprocal. So multiply by 5 over 1, and we get 5. So that's a quick fraction refresher there. 1/5, we get 5. 1/3, we get 3. And if we plug in a big number like 20, we get 1/20th. All right, so I skipped 0. Does anyone have a thought on why I skipped 0?
Because it doesn't really come out to anything useful.
Yeah, it's undefined. It doesn't make sense right here. Yeah, so 0's is not in the domain. Yeah, so we can't divide by 0. That's really important. We can't divide by 0, so 0 is not in the domain of this function. All right, and then we can just plot the points we figured out. So it's like -1/10. All right, so we only did, I think there's a -1 in there as well. Okay, so we only plotted 7 points, but already we can kind of see the shape of it. So it will connect smoothly like this. All right, and then now when we're approaching 0, we're actually going to get shot up like this. And when we're approaching 0 on the other side, it's just going to continue going down. Does anyone have a thought on why that's the behavior that we would expect to happen? Or like why a small number is going to give us a big number out of it? Okay, so maybe that was a confusing question. Matea said 0 isn't in the domain, and it's, yeah, so 0 is not in the domain. And I think what's happening is that when you're like taking a small number, so if you take any small fraction, take like 1 over 1/1000, all that does is you just flip the way the fraction looks. So you just get 1000 out of it. So as we plug in these small fractions, we're just flipping them. So a small fraction becomes a big fraction when you flip it over. So that's what's happening. And then the negative only looks negative because there's also a negative sign in those numbers. All right, and then when we're moving out for the end behavior, now our function's starting to approach 0. And that's because when we're taking 1 and we divide it by a big number, in like elementary school or middle school math, when you have 1 and you're dividing it by a number, you can think of it as you're like cutting a pizza into a lot of slices, a lot of even sized slices. So those slices would be very thin and very small. So like 1 divided by, we plugged in 1,000 to this function, we get 1 divided by 1,000, which is 1,000th, which is a very small number. So this function takes small numbers and gives us big numbers, and then takes big numbers and gives us back small numbers, which is a little different than like what the polynomials usually do, because polynomials were giving us, usually for big numbers, we were getting the end behavior where it'd give us a big number out of it. But now we're plugging in big numbers and we get a small number out of it. Okay, so we're going to introduce 2 new pieces of terminology. The first is called a vertical asymptote. And so usually we'll represent it as just like a dotted line. If it's going through the axis, sometimes it's just easier to see it doing like the side dashes as well. So a vertical asymptote is just a line that our function starts to approach. So our function gets very close to this vertical line. So that's why it's called a vertical asymptote. And then we have a similar line down here. Can anyone guess what this line would be called?
Horizontal asymptote?
Yeah, exactly. It's a horizontal asymptote. And again, it's just a line that our function is trying to approach. So I wrote down here that an asymptote can kind of be thought of as like a trend line, kind of what like the function settles down to, or it kind of captures like divergent behavior. So like this horizontal asymptote is something that the function is trying to get close to and just settle down to. The vertical asymptote represents like what we'd call like divergent behavior, but it's just like the function's going off to infinity or negative infinity, and the line is just blocking what's actually like not letting the function cross. And this kind of makes sense with our like the intuition that some people say that like 1 divided by 0 is infinity. At this level, that's like not correct to say. But in some like later parts of math, actually a subject called complex analysis, it turns out to be very beneficial to look at functions and at these rational functions and see where they evaluate to infinity, like you'd get like a number divided by 0. Oh wait, but so for right now, we'll also just think of vertical asymptotes and horizontal asymptotes as providing a frame for our function. So we can kind of see that the vertical and horizontal asymptotes, they split up the graph into 4 regions. And in 2 of the regions, nothing is happening with our function. And in 2 of the other regions, very similar behavior is happening. All right, and we'll get a little bit more rigorous mathematically down the road on what vertical asymptotes and horizontal asymptotes are, how we find them, and how they work. But right now, I just wanted to give a brief introduction to what they are and why they come up on the graph. All right, does anyone have any questions at this point? I think everyone should be a little bit confused because we're just like introducing a new topic and this is more of like a high level explanation. But does anyone have any questions? Okay. All right, so I wanted to give an example of where a horizontal asymptote can come up. Again, this is playing with this idea of like a horizontal asymptote represents a value that the function kind of levels off to. So for this example, I was thinking about driving my car onto the freeway. So back when I lived in California, I used to drive from my parents' house to my school. A lot, it was like some weekends I'd go home and I'd have to drive back and it'd be like a 150-mile drive. And I think I'd get like, my car would average 27 miles to the gallon. But at every point in time, I wasn't getting 27 miles to the gallon. So it usually looked like, well, I'd start off at time 0, my car's not on, it's not moving, so I'm getting 0 miles to the gallon. So at the origin, we're at 0. And then over time, not really moving, or then I start moving. I have to drive through my residential neighborhood with a lot of stop signs. So the mileage is pretty low. And then maybe I get stopped at a stop sign, so it goes back down to 0. And then to get to the freeway, I actually have to drive down a pretty large hill. So my gas mileage spikes way up. And then it comes down as I slow down to get on the freeway. And then it starts to level off around 27, as then I just start to cruise on the freeway. So this is this kind of function is something that you might want to model with a rational function, because it sort of looks like it's going up and down, and then it like levels off at this horizontal asymptote at 27. And it's also like a trend line as well, in the sense that even when I'm on the freeway, I'm not always going to get 27 miles to the gallon. There's hills that I have to go up or go down that would improve or lessen my gas mileage. But yeah, so that 27 inch is just like a trend line. So that's what our horizontal asymptote is trying to catch. All right, questions on this example of a horizontal asymptote? Or is there anything anyone's wondering at this point? Okay. So now I thought we could look at an example with the width of a rectangle of area 1. This is where a vertical asymptote can come up. So I was thinking that maybe you have some kind of, we could put like a story behind this. You're designing some sort of farm. The government gave you a square mile of land, and you get to decide how that land looks. So you're trying to determine, so if you know the length, you can also determine the width, because the length times the width equals the area. So we can determine the length, and we know the area has to be 1. So if the length was 1, then the width would be 1. So this point is on our graph. But maybe we don't want to devote that much length. If we only had half the length, we'd end up doubling the width. Or halving the length again. So maybe we have a fourth, and now the width would have to be up here at 4. So we get some behavior that looks kind of like this. And I guess this would keep going down like that. And so we get this vertical asymptote here at 0. And so the reason for that is that we can't actually have like a width of 0. All right, so let's do a quick check. If we're trying to make rectangles that have area 1, why can't we have a width of 0? Or a length of 0?
Because the area is the length times the width, and if you multiply by 0, you get 0.
Exactly. Thank you. Yeah, so straightforward as that. We can't have like a length of 0. But yeah, also the area is just the length times the width. So, if the length was 1 over, I don't know, here's a big number, 1 over 100 billion, could we still make a rectangle of area 1? What width would we need? Does someone have an answer? All right, well, it's just 100 billion as well. So you have 1 divided by 100 billion times the width of 100 billion. You just get a rectangle with area 1. And so that's kind of what I was drawing down here, where we have, it could look like this. It could look like this 1/2 and 2. 1/5 and 5, it's a little like out of hand. And then what's really out of hand is something that looks like 1/1000th by 1,000. It just looks like a straight line. So yeah, so that's kind of how a vertical asymptote happens. When you have this behavior that you can make it work by having one thing really small and one thing really big, but you can't actually go all the way down to 0. Okay. All right, so hopefully everyone's been watching the lecture videos as well, because I think, so one thing with rational functions is there's a lot of pieces to them. And it is hard to go over everything that there is to go over just during class. Even before quarantine, when I was doing class in person and doing lecture video and not doing lecture videos, doing lecture in person, it was very difficult to get through all the different features of rational functions. So I just wanted to give everyone just a heads up that we do need to make sure that we're like watching the lecture videos on time and putting some effort into them. And yeah, so I also have this warning right here too, that they're complicated. And we're going to start looking at what is a rational function, what isn't, and then how to graph them. And graphing them adds a few more steps than just graphing polynomials. And then just like a last thing that I do want to stress with these is rational functions, they aren't hard, they're just complicated. We're not taking anything to like any level that's harder than what we were already doing with polynomials. We're just making a function that's more complicated. So almost everything we'll see in here is stuff that you've seen before. There's just some more steps. So yeah, my little like example is that hard doesn't equal complicated. Running a mile in under 4 minutes is really hard, but in theory, it's not complicated at all. You just go out and you do it. It's hard getting to that speed, but it's not that hard to do once you can do it. Whereas like making cookies it's not that complicated, but it's kind of complicated. You have to follow a recipe usually. But no one would describe that as hard. There's just a lot of steps to remember. So rational functions are going to be a little bit more like making cookies rather than running a 4-minute mile. So anyone can make cookies. It just takes there's just a lot of steps to it. So yeah, just devote some time to mastering rational functions. This isn't something to put off for a couple weeks. I think this is something that like this week is a good week to just catch up with the lecture videos and spend a little extra time thinking about rational functions. And I think it will really reward you for it. All right, so let's jump into what is and isn't a rational function. All right, so we have that a rational function is a function that looks like a polynomial divided by a polynomial. So this first one, this f of x, is this a rational function? Yes or no? Let's do the thumbs up reaction for yes and the clapping reaction for no. All right, just do the reaction. All right, so there's some disagreement. Let's see, to anyone who doesn't think this is a rational function, give me a reason why you're thinking it's not. Or anyone who thinks it is a rational function, can you give me a reason why you think it is a rational function?
You had mentioned that a rational function was a polynomial divided by a polynomial. So, I mean, just reading that in English, that kind of says that. So that's why I would say it is.
Okay. Yeah, thank you. Yeah, so all we do is we just look at the top, we look at the bottom. They're both polynomials. So it's a rational function. All right, so what about this, the g of x, this 2x plus the square root of x divided by 1/2 x minus 1/2. Let's again do the thumbs up if you think it is a rational function and the clapping if you think it is not. Okay, so again, a little bit of disagreement. I think for the essence of time, I'll just give this one away. This one ends up not being a rational function since 2x plus the square root of x is not a polynomial. So that was one of our things with polynomials where we have to have them, like the square root of x is the same as x to the 1/2, but we have to have our x's to integer powers or positive whole number powers and not these fractional powers. So this one is not a rational function. All right, and let's do the final one, h of x now. So again, thumbs up if you think it is a rational function, and clapping if you think it is not a rational function. Okay, so I think almost everyone said they think it is a rational function. Can someone who thinks someone who thinks it is a rational function, can you tell me why you think it's a rational function?
There's no fractions and no square roots.
Yeah, there's no fractions, there's no square roots. The thing that I'm concerned about is that we needed to divide a polynomial by a polynomial. But here we have a polynomial divided by a polynomial plus a polynomial. Is that okay?
Not according to the definition.
Yeah. Okay, so not according to the definition right there, but is there a way that we could make it look like the definition? Does someone have a thought about that?
Could you just add 2x to the top and bottom? Like, and then that makes sense. Just put 2x on top and bottom.
I like the way you're thinking, but that's not quite how like
Turn 2x into
fractions
a fraction.
What was that, Adam?
Turn 2x into a fraction.
Yeah. So like Lillian was saying, she wanted to add like it to both the top and the bottom. So yeah, when we're adding fractions, we want to do we want to make that common denominator. So that would be doing 2x times x to the 5th divided by x to the 5th. And then when we have that common denominator, we can add them together. So we get 2x to the 7th plus 2x, the x and the x to the 5th become x to the 6th plus 1 over x to the 5th. So it turns out that this is a rational function. But I think, Aaron, you said you didn't think it was. I think that was smart to think that it wouldn't be because it doesn't follow the definition. So this is just kind of a tricky one where it doesn't look like the definition. So we have to do a little work to make it look like it is the definition. So yeah, so this one ends up working, and really we can do this with, like there's nothing special about 2x. So if we have like a rational function, we add a polynomial to it, that'll always be fine. All right, let's do one more thing here. The other thing that I wanted to talk about actually is domain. And before we talk about domain, are there any remaining questions about determining if this is a rational, if these are rational functions or not rational functions? Okay. All right, so in our domain, we knew with polynomials, the domain was always all real numbers. So for this whole class, we haven't really focused on the domain, but probably in 1108, you did focus on the domain a little bit for other kinds of functions. So what could go wrong with rational functions where we might have to worry about the domain? Someone have a thought?
Might have to divide by 0.
Yeah, exactly. So rational functions, we could divide by 0. So we need to be careful that we never divide by 0. So we need to make sure that we don't include the numbers in our domain that could have us divide by 0. All right, so let's look at this first rational function. Keep the information that is a rational function. So what number could we end up plugging in with this function that would make us divide by 0?
-1.
Yeah, exactly, and just -1. So if we plugged in -1, we'd get, we don't really care what the top is when we're determining domain, but the bottom would be -1 plus 1, which is 0. So that's the only number we need to worry about. So we can write our domain as, we can use the all real number symbol. Oh, not 0. Take out -1. So this is one way to write it. This is the set difference notation, where you take all real numbers, and then here the minus sign just means except. So all real numbers except -1. Or we can write it in the interval notation. Personally, I like this set difference notation. I think it's really clean. The interval notation is also always a perfectly fine answer. And then I guess the third option is you can do this greater than or less than way of doing it. So x is less than -1, comma, x is greater than -1. So that's 3 ways that we can specify the domain. And yeah, you're welcome to use any any way you want for this class. Well, I guess one of these three ways is probably what's expected to use. All right, so we're not going to do anything with the domain of g of x since it's not a rational function. But let's look at h of x. What numbers could go wrong with h of x? So where might we end up dividing by 0? Like what number could we plug in that would cause us to divide by 0?
0.
Yeah, thank you. Yeah, just 0. So again, like we'd plug in 0 for that top polynomial. We don't really care what that value is. Nothing's going to go wrong there. But then we divide by 0 to the 5th, which is still just 0. So we have to take 0 out of the domain. So our domain is, again, r minus 0, or you could do something like negative infinity to 0, cup 0 to infinity. Add some space here. So to find the domain, so always just to find the domain, we just need to find the roots of the denominator. So that's in f of x and h of x, that was pretty straightforward to do. We'd also be able to handle it if we had something that looked like k of x equals this. Then we just look for the roots of 2x squared plus 5x plus 1. So this is still doable. And yeah, so any polynomial we have, we just need to find the roots of it. So then to determine the domain of a rational function, we just need to worry about how do we find the roots of a polynomial. And thankfully, that's what we just spent the whole last chapter working on. So that information is going to carry over right into this. All right. Questions on the domain?
This isn't a question on the domain, but I just am missing something in my notes. Can you go back up to the graphing portion so I can make sure I get the right stuff written down?
Yeah. Which graphing portion?
Where it was listed, like right there. Perfect. Thank you. All right, I got it. Thank you.
All right. You're welcome. Okay. So now we just need to talk about one last thing. I think this is the last. Yeah, so this is the last section in the notes for today. And it's called reducibility. So with regular fractions, we have reducible fractions and irreducible fractions. And so essentially a fraction, when we're looking at like integer fractions, it's reducible when you can divide out like a common term from both the top and the bottom. It's like if we had, so we can write 2/3, and that's considered irreducible, but if we had 4/6, we could write that as 2 times 2 over 2 times 3, and then cancel out these 2's and end up with just 2/3. So we get something simpler. So it's irreducible. Irreducible is the simplest. And if it's reducible, it could be simpler. So typically people don't like irreducible, or people don't like reducible fractions because they're unnecessarily complex. Like if you say 4/6, now you're just making someone deal with 2 bigger numbers, whereas like 2/3 are 2 smaller numbers. All right, well, the same thing is going to happen with rational functions. So on the left, we have a rational function that's reducible. And this one's like clearly reducible. We have an x minus 1 times x squared divided by x minus 1 times x plus 1 cubed. So it's easy to see that we should cancel out the x minus 1's and just replace it with this simpler function. I said it was like straightforwardly reducible, and that's because sometimes you'll have something that's less straightforwardly reducible. You might have something that looks like x minus 1 over x squared minus 2x plus 1. So if it's expanded out like this, it's not clearly reducible, but we could factor the bottom as x minus 1 squared, and then see that we can reduce that to just x minus 1. 1 divided by x minus 1. But yeah, so the takeaway is that the same thing we can do with regular fractions, we can also do with these rational functions, which is canceling out common terms. We have one difference with ours, and that's, or maybe 2 differences, and that's going to be graphing and the domain. All right, so can someone tell me or give me a suggestion on how they think the domain of these 2 functions might be different? There's one difference. Does someone have a thought on what it could be?
Be a negative and positive sign.
Yeah, so there's that negative and yeah, so one has an x minus 1 and one doesn't, but how is that going to change the domain?
Would it invert it?
It actually just adds, but yeah, thank you for guessing. I think that, yeah, it also adds in like this, both of them have this r minus 1, but this, because it has a minus sign here, it also means the opposite of minus 1 is in there. So we get 1 in there. So this representation, call it function 1 and call this one function 2. Function 1, because it's reducible, actually has fewer points in its domain. We have to take out an extra point. That doesn't work. But in function 2, we don't have to worry about that. And then when we're graphing these, we get, let's call this one the graph of function 1, this one the graph of function 2. Now I'm going to draw a graph that won't be obvious to anyone, but that's okay. It's going to look something like, it has to have a root at 0. right, so everyone's going to end up watching a whole bunch of videos on how to graph these functions, and you'll understand why it looks something like the way it does. But the thing to focus on right now, that the difference is that this graph of function 1 has what we call a hole. So it's a point that could be evaluated, maybe it should be evaluated, but if we plugged it into this function, we'd get that it's undefined. But when we look at the reducible function or the irreducible version, there's no hole. So this hole is just saying that our function is needlessly complex. It can be simplified in some sort of way. Yeah, so that's just what's going on with these reducible functions. And pretty much we're always going to assume that the function is irreducible. I'll try to present functions in a way that are irreducible. But you might be asked a question on an exam. Like does this function have any holes in it? And it would mean like, does it have like one of these holes that show up?
Does that mean that every function that has a hole can be reduced, or is that only in some cases?
Every function that has a hole can be reduced. So yeah, the holes end up coming from behavior where we have like the top is going to 0. So as we're getting close to 1, this top number is pretty close to 0 because a number close to 1 minus 1 is pretty close to 0. And the bottom's pretty close to 0 for that same reason. And so they sort of balance each other out. But with other problems in our domain that we might have, they're going to actually give us vertical asymptotes, which is going to be our first topic on Wednesday. But so whenever that can't be reduced, we get behavior that looks like this vertical asymptote behavior. That was a good question. That's always a good thing to ask in math. If you can do it if you can do it in a couple instances, can you do it in every instance? That's always a good question to ask. All right, so that's it for rational functions today. Are there any questions?